Hello, Matthews Gatos here. Welcome to Chapter 6, Trig Identities. In this video, we're going to cover 6.1, which is the beginning of understanding all those formulas on your formula sheet, that big chunk of trig formulas. We're going to cover reciprocal, quotient, and Pythagorean identities. So I want to talk about, first of all, what does it mean to verify an identity? So an identity is something that's already been proven. Something like a squared plus b squared equals c squared. That's an identity. So how do you verify that, just to even see if it might be true all the time? Well, one way is by substituting. You can substitute specific values of x into the original equation. Now, if the left side equals to the right side, it's verified, but only for those particular values. Another way you can do it is by graphing. So you can graph one side of the identity in y1, the other in y2, and see when you hit graph, do I only have one graph? And if I do, it has been verified graphically. But I can't stress this enough. Verifying is just that. It's checking to see if it's true for those values, but it doesn't mean that something is proven. So let's just practice how to verify, because that's an important strategy. If you verify something and you find that it's not true, then you don't have to prove it because it's just not true. So let's verify this identity here, that cotan x times sine x equals cosine x. We're going to verify it first of all for 60 degrees. All that means is I'm replacing my x with 60 degrees and seeing if it works. So cotan is 1 over tan, so 1 over tan 60 times sine 60, that's 0.5. And on the right-hand side, I get cos of 60, that's also 0.5. My mode obviously is in degrees because I have 60 degrees. Since the left side equals to the right side, I have verified it. So left side equals right side, so it is verified. Done. Okay, let's look at if I did pi over 3. So pi over 3 in radians. So same idea that I did before. I'm just putting in pi over 3, so my mode has to be in radians. And you can see that the left side equals to the right side again. So since left side equals right side, it is verified. And again, all I've done is checked that it's true for those specific values. Okay, let's try doing it graphically. So checking. So if I wanted to check this on the graph, I could put the left side into y1, the right side into y2. So you see cotan 1 over tan times sine. I have to write it as 1 over tan because there is no cotan button on my calculator. So you only have the primary trig ratios of sine, cosine, and tangent. They're kind of like your primary colors. You can make secondary colors from them, but you have to only come back to those three. Same thing here. So 1 over tan times sine equals, and then the other side, cosine. So you can see in your table of values that they're equal for all the permissible values. But I see a whole bunch of errors. Why are there so many errors in y1? Well, in y1, if you'll notice, there is a fraction. So I have 1 over tan of x. So anytime that denominator is 0, then I'm going to have a restriction. So let's look at that denominator. I have 1 over tan x, which is really 1 over sine over cos. So I have a restriction that cos x can't be 0, which is why I have restrictions at 90 degrees and 270. But because sine is in the numerator of the denominator, if this numerator was 0, then the whole fraction would be 0, and I'd also be dividing by 0. So that's why I also have a restriction at 0 and 180. So that's why they're errors. So when we prove something, which we're going to get to a little bit later, we're proving it true for all permissible values. So we only look at the ones where it actually works. Now, non-permissible values are a really important idea, so I just want to review some of those non-permissible values. Okay? So non-permissible values, division by 0 is not allowed. So sine and cosine, there is no division for sine and cosine. So these are actually the only trig ratios that have no restrictions. Let's look at tangent. Tangent is the ratio of sine over cos. So since cos is in the denominator, it can't be 0. Cotan is the ratio of cos over sine. So sine is in the denominator, so sine can't be 0. 1 over sine, again, sine is in the denominator, so sine can't be 0. And cosine, secant is 1 over cosine, cos can't be 0. Now you'll notice for our our 4 ratios other than sine and cosine, all of those restrictions have to do with sine and cosine. And in fact, the majority of trig non-permissible values involve sine or cosine not equaling to 0. Not all of them, just the majority of them. So we really need to be comfortable on knowing, and I suggest committing to memory, when sine and cosine are equal to 0. So let's look at when sine is 0. So when sine is a factor in the denominator, sine can't be 0. So anytime sine is 0, there's going to be a restriction. So if you look at a sine graph starting at 0, the next x-intercept is pi away, the next x-intercept is pi away. Same thing in the other direction. All of the x-intercepts are pi away. So starting at 0, restrictions happen every pi radians in both directions. So the restrictions for sine are that x cannot equal to multiples of pi, where n is an integer, meaning I can have positive and negative factors of my restriction. Let's look when cosine is 0. So anytime cosine is a factor in the denominator, cos x equaling to 0 will cause a restriction. So looking at the cosine graph, which has just been shifted over, I have a restriction starting at pi over 2, every pi radians apart in both directions. So starting at pi over 2, the restrictions happen every pi radians, again in both directions. So x cannot equal to pi over 2 plus multiples of pi n. And again, n is an integer, meaning it's positive and negative multiples. So let's go back to that question that we just did. And instead of stating our restrictions in terms of sine and cosine, let's state them in terms of the restrictions themselves. So again, sine and cosine have no restrictions. So tan has a restriction where cos can't be 0. Cos is 0 starting at pi over 2 and multiples of pi n. So this is the restriction for tan. Cotan, sine is in the denominator and it can't be 0. Sine is 0 with multiples of pi. Cosecant, 1 over sine, so sine can't be 0, which means x can't be multiples of pi. Secant, 1 over cosine. Cosine can't be 0, so my restrictions are pi over 2 plus multiples of pi n. So the restrictions for sine and cosine are actually happening on the unit circle at all of the quadrantal angles. These are where all of my restrictions are. So the restrictions happen at the quadrantal angles. Now let's talk about the unit circle for a minute. When we developed the unit circle, we said that the equation of the unit circle was x squared plus y squared equals 1, because 1 was the radius. And that was true for all points on the unit circle. So if we have x squared plus y squared equals to 1, and x is cosine and y is sine, instead of saying x squared plus y squared equals 1, the equation of the unit circle, I can say that cosine squared plus sine squared equals 1. And this will bring us to our very first Pythagorean identity, and probably the most important one. This one comes up a lot. So, putting this all together, here's my first Pythagorean identity, and this is how it appears on your formula sheet. Sine squared plus cos squared equals 1, or cos squared plus sine squared equals 1. It goes both ways. So you can see it this way, or you can of course see it this way, because addition is commutative. It can go both ways. So sometimes you're not just going to see it as cos squared, oopsie, plus sine squared, or sine squared plus cos squared. Sometimes you're going to see it in terms of cos squared or sine squared. So I just always like to rearrange these so you have all the different ways you could see the Pythagorean identity. So isolating for cos squared, that would just be subtracting sine squared from both sides. This would be a derivation of the original Pythagorean identity. Isolating for sine squared, that would just be subtracting cos squared from both sides. I could also have that it was 1 minus cos squared. So those are 3 different forms of the same Pythagorean identity. Now this identity is so important that the other two identities follow from it. So let's say that we were to take our Pythagorean identity and divide everything by a sine squared, or in other words, like kind of like factoring out a sine squared. So if we were to take this and divide everything by sine squared, let's look at what we'd end up having. So sine squared divided by sine squared is 1, plus cos squared divided by sine squared, well, that's just cotan squared. And 1 over sine squared is cosecant squared. So this will give rise to the second Pythagorean identity. So I always think it's really important that you guys know where these come from. So this again is on your formula sheet. You don't have to memorize it. I just wanted you to see where it actually comes from. So 1 plus cotan squared equals cosecant squared. So that's the Pythagorean identity. Let's just write it in terms of cosecant squared. Flipping it around would be 1 plus cotan squared. And in terms of cotan squared, I would just subtract 1 from both sides. So those would be my two identities written in terms of cosecant squared and cotan squared. Now, for this one, I divided by sine squared. Let's look at taking Pythagorean identity number 1 and dividing it by cosine squared. We already did sine squared. Now we're going to do cos squared. Okay, so cos squared divided by cos squared is 1. Sine squared divided by cos squared is tan squared. And 1 over cos squared is secant squared. Okay, so this is Pythagorean identity number 3. So 1 plus tan squared equals secant squared. So just rewriting that with secant squared, the other flipping it around. So secant squared is going to be the same as 1 plus tan squared. And then to solve for tan squared, I would just subtract 1 from both sides. So secant squared minus 1. So these are on your formula sheet. I just wanted you to recognize that they could be rearranged, and sometimes you only look for it in one way, but it can appear in another way. So these are all of our trig identities so far. So tan we already knew, ratio of sine over cos, cotan ratio of cos over sine. We talked about the reciprocal identities already, and these are your 3 new Pythagorean identities. So these can be used to prove any other identity, but just remember, that's why I took you through those. All of those identities can be rearranged and written in terms of another variable. So before we get into proving trig identities, which is the end of our chapter, we need to practice how do we simplify a trig expression, because that's all an identity is 2 expressions that are made equal. So here are some of the ways that I have found that it works to simplify trig expressions. This is by no means an exhaustive list. This is just kind of what I mentally go through every question, and I try to run through, oh, I'm going to try this, or I'll try that. The very first thing I always try is I try to write things in terms of sine or cosine. That usually works, I'd say about 80% of the time. Then I also look for, is there a GCF? Is there something common to all the terms that I can factor out? Can I combine the fractions, adding them with a common denominator? Can I multiply numerator and denominator by a conjugate? I look through all of those different ways, and I always have my formula sheet right beside me so that I can refer to those just to see, is there a formula that can help me? And always remember to state your non-permissible values. Now this last one, you might be wondering, like, what are you talking about? Multiply by the conjugate. I didn't think we were talking about roots. And we're not, but the principle of conjugate that we learnt in radicals works here as well. So all a conjugate is a way to create a difference of squares. That's what a conjugate is. It's a difference of squares. So a conjugate is based on having a binomial factor and multiplying it by another binomial factor with an opposite sign in the middle. So the terms are the same, it's just the middle operation that gets changed. So for example, if I had a minus b, the conjugate a plus b. If I have a plus b, the conjugate is a minus b. So when all else fails, if you have a binomial term, there's nothing else you can do, you can always try to multiply it by the conjugate. Now remember, you only want to expand the conjugated part. So if I'm trying to multiply by the conjugate of the denominator, I only expand the denominator. The reason is, by only expanding the denominator and keeping the numerator in factored form, there's usually a way to simplify it further that would be easier if you left it factored. Okay, so let's jump in and try some examples. So cotan theta multiplied by cos theta. So I'm going to go to my first strategy I always go to, write it in terms of sine and cos. So I'm going to write this as cos theta over sine theta multiplied by cos theta. Let's just put that over 1 so it's also a fraction. So looking at this, I see that I have a sine squared in the denominator, which means sine can't be 0. And if sine can't be 0, then I know that my restriction is that theta can't be multiples of pi. So I've stated my restrictions. Let's go back and simplify. So cos times cos in the top is cos squared. And sine times 1 in the bottom is just sine theta. Okay, and that would be as far as I can go. Let's try another one. So this one here, I'm going to go again, and I'm going to write everything in terms of sine and cosine. So sine theta plus cotan, which is cos theta over sine theta. And I'm going to multiply that by cos theta. I'll put it over 1, so it's also a fraction. So looking at my denominator, I can see that I have a dividing by sine. So since I can't divide by sine, I have a restriction that theta can't be multiples of pi n. Okay, so back over here, I'm going to have sine theta plus cos squared theta over sine theta. Okay, so doesn't look like I can do anything else with the sine. Sorry, that's sine theta, not sine squared. Okay, it doesn't look like I can do anything else because they're all in terms of sine and cosine. However, I am adding, so I could add using a common denominator. So let's put that out of 1. Common denominator here would be a factor of sine theta. Okay, so over here, I would multiply this by sine theta. And to be fair, multiply the numerator by sine theta. So I would get sine squared theta. This is already out of sine theta. Okay, so then what I have is sine squared plus cos squared out of sine theta. So I can add them as one big fraction now. Okay, and I hope you recognize this because this is the biggest Pythagorean identity that all the others come from. Sine squared plus cos squared is just 1. So 1 over sine theta. I can go even further because 1 over sine, that's a reciprocal identity, is cosecant. So that would be my final answer. Okay, let's try another one. So I have cos over 1 minus sine. So much for my strategy of writing things with sines and cosines because it's already a sine and cosine. Let's talk about the restrictions before we figure out what we're going to do with this. So in the denominator, I have 1 minus sine theta. So 1 minus sine theta can't be 0, which means sine theta can't be 1. Now if you think on the unit circle, or even on the graph, depends on how you think of sine. Sine is 1 at 90 degrees, and it will be 1 again by multiples of the period of 360. So it's going to be 90 degrees plus 360n. Okay, so now that I've stated my restrictions, let's see what else I can do. So I've already written it in terms of sine and cosine. It's already like that in the original question, so that doesn't help me. I can't add the fractions. There's nothing to add. So this is where that strategy of conjugate comes in, kind of when all else fails. Like I can't do GCF. It's already in terms of sine and cosine. I can't add fractions. I can't break it apart into two different fractions. So this is where I'm going to try conjugate. So I'm going to multiply denominator by the conjugate. So I'm going to have cos theta over 1 minus sine theta. So I'm going to multiply the denominator by the conjugate. And the conjugate is just the same terms, opposite sign in the middle. So if I do it to the denominator, I have to do it to the numerator. Now I'm doing this for the benefit of the denominator. So I'm going to leave my numerator factored. Leave it just like that. And then I'm going to expand my denominator. So applying the distributive property, 1 times 1, 1 times sine theta, negative sine theta times 1, negative sine theta times sine theta. Okay, so you can see my middle terms are gone. So leaving my top term factored, cos theta 1 plus sine theta, all over 1 minus sine squared theta. Well, 1 minus sine squared theta, that's one of the rearrangements of Pythagorean theorem identity number 1. And 1 minus sine squared is just cos squared. And you can see now why I left my numerator in factored form. So I have cos theta and cos squared can cancel out. And I'm left with 1 plus sine theta over cos theta. Now, that doesn't look a lot different than what I started with, does it? Because I've just I have a binomial in the numerator, a monomial in the denominator, when I started with monomial over binomial. It doesn't look that much different, but because I have a monomial denominator, I can actually separate this into two different fractions now. I can separate this into 1 over cos theta plus sine theta over cos theta, because they all have a common denominator of cos. Well, 1 over cos is just secant, and sine over cos is just tangent. So this would be my final answer. So this is another trick that we can add to our repertoire when we have a monomial denominator. So anytime we have a monomial denominator, we can separate into two different fractions. So if I have a binomial numerator, a plus b over c is really a over c plus b over c. Now that only works when I have a common denominator. Please don't try to separate them into something like this, a over b plus a over c. Those are not the same because this has no common denominator, so you cannot do that. But when I only have a monomial denominator, that's a good strategy that I can use. Okay, let's try another one. So I have secant squared minus 1 over secant squared. So this is where having your formula sheet out is handy, because secant squared x minus 1 is a rearrangement of one of our Pythagorean identities. Secant squared minus 1 is actually the same as tan squared. So this is going to be tan squared over secant squared. So now that we've done that, let's write it in terms of sine and cosine. So this would be tan squared is the same as sine squared over cos squared, all over secant squared is 1 over cos squared. Okay, so anytime I have a fraction over a fraction, I want to get rid of the fraction by multiplying by the denominator. So if I would multiply this by cos squared, it would get rid of the denominator. But if I've done it to the numerator, I must also do it to the denominator. And that looks good because it also gets rid of that denominator. So if you look at this, cos squared and cos squared cancel. I'm just left with sine squared in the numerator. Cos squared and cos squared cancel. I'm just left with 1. So sine squared over 1 is just sine squared x. Now, I forgot to state my restrictions, so I need to back up the bus a little bit here. If I look at my denominator right over here, I have a cos squared in the denominator and a cos squared in the denominator. So I have a restriction here that cos can't equal to 0, because if cos was 0, well then cos squared would be 0. So cos cannot equal to 0. So looking at my restrictions, cosine is 0 here at pi over 2. So it's going to be pi over 2 plus multiples of pi n. Okay, we have one more question to do. Let's look at this one here. So I have 1 minus cos squared times cosecant squared. Now the temptation is to apply the distributive property, isn't it, to multiply those together. But I'm not going to do that because I recognize that 1 minus cos squared is the same as sine squared x. So this is why I got you to rearrange all of those Pythagorean identities so you're able to recognize the different forms. So sine squared times cosecant, which is 1 over sine. Let's make that one over 1 as well. So you can see now my denominator, sine x, can't be 0. So if sine x can't be 0, I'm going to have a restriction right here that x cannot be multiples of pi. So let's simplify this. Here I have a sine squared in the numerator that can cancel with one of the sine factors, and then this just ends up being sine x as my final answer. Okay, so to summarize this lesson, the majority, not all, the majority of restrictions have to do with sine and cosine not being 0, so I definitely think those are worth remembering. When you're simplifying it, you can see that the majority of questions that I did, writing in terms of sine and cosine, usually worked. The other strategy that came up was being on the lookout for Pythagorean identities, even if it's rearranged. Here's what I look at. If there's like a binomial and one of the terms is squared, I always look to see, is that a Pythagorean identity rearranged? And then looking for the GCF to simplify, or multiplying by the conjugate. Those are all really good terms. So I thought this was a really cute cartoon. Doctor and nurse working. He's too big. We need to perform a square root a squared plus b squared section. Well, I hope you recognize what that is. A squared plus b squared equals c squared. The square root of c squared is a c section. So there you have it, the birth of a right triangle by C-section. Okay, so I hope this video helped, and you guys can go and do practice questions 1 to 3 in my notes. Of course, all the detailed solutions will be on D2L for you, and I will see you for the next video.